Okay, my friends, let's see if we can't do a common titration type of a problem here. We're going to take a certain mass of an acid here, in this case phosphoric acid, which we're told is a triprotic acid. We didn't need to know that because we can see those three acidic hydrogens right there. And we're going to try to dilute that. And we want to know the volume of sodium hydroxide of this concentration of sodium hydroxide that we're going to use to do that titration. Okay, we can do that. I use these steps right here. These steps are the steps I use actually to solve almost all of my ALEKS, my chemical problems that I'm posed with. I always make sure I understand the chemistry going on. I write a balanced chemical equation. I write down my conversion factors. In this case, I'm going to use molarity. I'm going to understand molarity. Molarity is a big M. I don't like that always. I like to say moles per liter because that is the definition of molarity, is moles per liter. Then I'll set up my dimensional analysis, making sure that my units make sense to me and that they'll cancel each other as I move along. And just as a little hint, I never start with a conversion factor. Okay, so let's do that. Let's write a balanced chemical equation that's going on, because again, we're doing this titration reaction where we're going to dissolve our acid in a little beaker here. And when we dissolve an acid, then these hydrogens are going to come into solution. And I want to often know, if it's an unknown, I want to know how much is in there. But in this case, we're calculating the volume of sodium hydroxide needed. That we're going to use a burette, and we're going to drip in there. So I drip in 1 mole, I drip in 1 hydroxide, and that's going to react with 1 of the protons that came from the phosphoric acid. And I do that over and over and over again until all of the hydrogens from this triprotic acid are consumed by the hydroxide. I want to know the volume that gets me to that final equivalence point. That's kind of the chemistry that's going on here. So let's go ahead and write a chemical equation right here. I have phosphoric acid H3PO4 plus the sodium hydroxide, and that always gives us the salt, which in this case is going to be the sodium phosphate, Na3PO4 plus my water here. Okay, so if I put a 3 right here, so that gives me 6 hydrogens. I need to put a 3 right there on my sodium hydroxide, and I think that's going to balance the whole thing out for me. So that gives me 7 total oxygens. That gives me 7 total oxygens. That gives me the correct number of hydrogens and my sodiums as well, my phosphates. This is a balanced chemical equation. Okay, so I've done step number 1. Now I'm going to write down my conversion factors. Okay, so I have 0.1600 molar, which is defined as a mole per liter. So much easier for me in my dimensional analysis to look at it this way. Now I have liters here, and I know that I need my answer in milliliters, so I'm just going to go ahead and write that conversion factor right now. So I do know that there are 1,000 milliliters in 1 liter. Okay, that helps me out. I'm given grams of phosphoric acid, and I wrote down the molar mass up here for later use. So I do know that there are 98 grams of phosphoric acid, PO4, so H3PO4 are in 1 mole. Okay, so I got moles. I'm feeling pretty good about where I'm going here. All right, so let's go ahead and set up that dimensional analysis. Sometimes it's hard to know where to start in these. I'll grant you that that's something to do. I never start with a conversion factor. Turns out that this 250 mils is just telling us the volume of the volumetric flask. I don't really need to use that at all. I'm going to start with that grams of phosphoric acid. And so I have 0.131 grams of phosphoric acid. Okay, I got to convert that to moles. I do almost nothing in grams other than weigh grams in the lab. I do all my chemistry in moles. So I do know that there are 98 grams in 1 mole of phosphoric acid, PO4. Okay, why do I write it that way? Because I got to get those grams to cancel each other out, and those are grams of the phosphoric acid. Okay, so I'm up to moles of phosphoric acid. Now I have to do the chemistry. We're trying to figure out the sodium hydroxide. Well, how do I get from phosphoric acid to sodium hydroxide in the stoichiometry? Well, I do know that for every 1 mole of H3PO4, I consume 3 moles of the sodium hydroxide. Okay, great. So now my moles of H3PO4 cancel each other out, and I'm left to moles of sodium hydroxide. Well, I need to somehow get to that volume. And this is where I can use that molarity. This is my molarity. I know that there are 0.1600 moles of sodium hydroxide in 1 liter of that solution. And then finally, it doesn't want the answer in liters, it wants it in milliliters. And so I also know that in 1 liter, there are 1,000 milliliters. And then my liters will cancel out. My moles of sodium hydroxide will cancel out. And the only thing that's left is milliliters of the sodium hydroxide solution. So if we actually want to get a number, which I will do, let me get out my calculator. I will take 0.131 divided by 98 times 3 divided by 0.16 times 1,000, and that's going to equal 25.063. This is going to be in milliliters. Now, why did I make an effort to tell you how I'm using my calculator? Because that's how I actually punch it in. I just work from left to right. 0.131 divided by 98 times 3 divided by 0.1600 times 1,000. If it's in the top, I multiply it. If it's in the denominator, I divide. Okay, so now I just have to worry about sig figs. I see 3 sig figs here. I see 4 sig figs here. That's all that's used in my calculations. And so the answer to this is going to be 25.1 milliliters. Okay, my friends, these are way doable. Get that chemistry right up first. Get it right. Get that chemistry right. Write down your conversion factors that you can foresee you using. Okay, change big M molarity to moles per liter. You should know in these that when we have a liter and we need to get to milliliters, we need that conversion factor. And oftentimes we'll need a molar mass that we get from the periodic table. Or you can look it up on Google. I do that a lot. And it's right most of the time, but not always. Okay, these are way doable. This is better than AI explanation and definitely better than the way that the good folks at ALEKS do that. Tackle it on yourself.